Former Twitter CEO Jack Dorsey has developed a new chat application that is decentralized, uses Bluetooth to chat with people nearby you. It is called BitChat, and some of the security claims have raised concerns in the InfoSec community, and researchers have been digging into this. We are going to discuss in this video some of the security flaws that have been noticed in the application, and we're going to write a fun little application to send some spam messages to people nearby you using a Python script that you could run on a little device like this, a Raspberry Pi. Plug a battery into it, put it in your backpack, have some fun. So, my name is Matt Brown. I love doing security research like this. We take apart technology, take apart devices on this channel all the time, and if that's something you're interested in, definitely hit that sub button, and let's get into it. The BitChat application, here it is. Here are the claims. End-to-end encryption. It's always good to have in bold. No accounts. That could be seen as a good thing for privacy reasons, or it could be seen as a bad thing. We'll get into that. And so, as you can see here, there's a lot of claims being made about this application and the protocol underlying it. This security researcher here, named Alex Radocea, I hope I'm pronouncing your name correctly, has pointed out that the key problem, there's a few of them, with this application is that the private message encryption functionality effectively uses what the website boasts are these ephemeral key pairs. Ephemeral just means that they change over time. There's no real trust relationship that is established, so there's no authentication. So when Alice talks to Bob, how does Alice know that she is talking to the real Bob and not an impersonator? So let's rig that up. I have not one, not two, but 3 phones running the Android version of the BitChat application, and so that's what we're going to be reverse engineering. And the source, it's open source, so it's not really reverse engineering, but we're going to be seeking to understand this system today. So right here, I have 2 phones. These are not emulators. These are right here on my desk, and so we're going to open the BitChat application on all 3 of my phones. So here I have Alice and Bob, and then over on this other phone I have Eve. So Eve is our attacker, our eavesdropper currently. So I'm gonna have Alice send a message to Bob, and then Bob is gonna send a message back so they can communicate. Currently, these messages are all in the public, no encryption. That is understood, and that is not a security flaw. These are public broadcast messages, and we can see here that obviously Eve can see all those messages because Eve is nearby, and these messages are broadcast to everyone. But if Alice goes ahead and goes up here into the private message feature and wants to send a message to Bob, this is Alice, and then Bob is going to get a private message here saying this is Alice, and we'll notice that Eve does not receive that message. And so this is a private message, and it is encrypted. But the problem is that every time you relaunch the application, the trust relationship the key exchange happens again. And so there's no way to know that the person claiming to be Bob that you talked to, yesterday is the person that you're talking to with the name of Bob today, right? And so if I, over here as Bob, I have to remember which one. Okay, Bob, I close out of the application, and so instantly it goes away. Alice sees that, oh, Bob's not on the network anymore. All right, let's open it back up. And so there's Bob again, but I don't have any of the messages, which that's kind of touted as like a privacy feature. Okay, I'm fine with the messages not showing up from the past. That's okay. But The problem with this, again, is what just happened in the background is another key exchange happened. And Bob here generated a brand new set of keys and then did the key exchange, right? So there's no way here for Alice to know that she's talking to the real Bob. And we can prove this. So again, we'll close out of that. And then we'll go over to our attacker phone here. And we'll just rename ourselves as Bob and say, hey, this is Bob. And so obviously, again, broadcast message, there's no encryption or anything happening there. So obviously, the attacker can change their username on the fly. Remember, there's no accounts, and that's touted as a feature, but that can also be a security problem depending on your context, right? Like, do you care more that your messages are deleted really quickly and you have this kind of ephemeral communication, or do you care that you can establish a trusted channel of communication with another individual, and then later you can come back and re-engage in that discussion and ensure that you are still talking to the person that you were talking to last time, right? And so we can see here that we just go to Bob here and then say, hey, this is Alice. That secret I have is 1, 2, 3, 4, 5, 6. Okay, so and then the application crashes because that happens all the time. But here we can see, that our attacker received this message as if they were Bob. And so that is, again, the fundamental problem with these ephemeral keys is there's no real trust relationship that's established between two people in their private messages. And so, so that is the exact flaw that was being discussed here in this article. So with that, we are going to now perform a little bit of, again, it's not exactly reverse engineering, it's going to, because we have the source code, but we're going to seek to understand the binary protocol that's being used to transmit all this data over Bluetooth Low Energy. And so the way we're going to do that is I've already obtained the packets off of one of these phones here, and I'm actually going to show you how I go about doing that. So on this phone, I can go here to, I always forget this, to system. I can actually show you with my mouse. And so I have already enabled developer mode, so just Google how to do that on your own phone. And there's a cool developer option in Android right here towards the top called Enable Bluetooth HCI Snoop Log. And so what that's going to do is all Bluetooth communications on the phone are going to be logged to a log file. And we can pull that log file off our phone. Again, Google that. Your mileage may vary whether your phone is rooted or not rooted. Either way, there's a way to get that file off there. It just may be more annoying if your phone's not rooted. But then what you can do is you can open that log file in Wireshark like we have here, which is really cool for taking a look at all these packets. And I already have a packet pre-selected that we are going to reverse engineer together. But just to kind of explain how I got here, I always use the BT-ATT filter in Wireshark, and that's going to filter down to Bluetooth Low Energy data packets. It gets rid of any of the advertising or any of the other stuff that's going across this bus. And so this zooms in really on what we care about if we're reverse engineering Bluetooth Low Energy stuff. And so here we can see we have a packet that it says sent handle value notification, and so it received this command from, and so in this case, this command actually is from my spam program, because there's a couple different ways to send messages, and this one sends it in a little bit simpler way. Both are acceptable, as we'll see, to send the messages. So what we're going to do here is I have this packet that was a handle value notification. Right here, we can see we have the value. So this is the raw data that's getting sent across Bluetooth Low Energy. And so I'm just going to simply go right click, copy, and then say as hex stream. So this is going to copy it as basically a hex string. And so what we can do with that is we're going to paste this into this cool tool that I've been checking out called IMHex. And so I will show you the repository or the website for this. So this is a super awesome tool. If you spend a lot of time reverse engineering binary protocols and tinkering with, with multi-byte objects and trying to figure out what they mean, this tool really helps you, and it looks nice. So that's always nice. So what I'm going to do here, I have a file open. And so I can simply click on this first byte here, and I can just paste. I can Control V right into here. And now we can see the hex, all this data. And what's really cool with this tool is as I click through here, over here, it's dynamically interpreting the data at that point and then potentially bytes after it. And it's using known data, like data types from known programming languages. Obviously, this is very like C oriented right here, these different data types. And so this can help you when you're reverse engineering, because if you kind of expect a certain value to appear somewhere in your data, then if you find that value in one of these interpretations, then you might know what data type is being used. So this is going to be really awesome. And here is the one thing, we're going to switch this over to big endian, because most of the time this is probably a good default when you're doing network-based communications, because another thing that big endian is usually called is network byte order. So data sent over the wire, so to speak, or over the air in this instance, is going to be big endian. So we're going to set that off the bat. And now let's go look at some of our code here. So obviously in here, we can already see some information that we care about, right? Like we can already see our message, right? That hello world was the message that I sent with the spam program. And then we can see Alice is the user, is like the username there. But we're seeing a bunch of other stuff here that we need to interpret, right? Like all this data right here, this is obviously not ASCII. And so we need to figure out what this stuff is if we want to send our own packet data that looks like this, and for it to make sense to the client that's receiving it. So what we're going to do is we are going to come over here, and we're going to look at a couple source files inside the BitChat Android application. And so the first one we're going to look at is this binary protocol. And so here is this packet specification. It says it is a fixed 13 bytes. And so again, we can see that the first byte is the version, the second byte is the type, and then we have a TTL, which if you're not familiar with network communication, stands for time to live. So this is a mesh network type of application where if your phone receives a message that's not meant for you, it can pass it along. And a very common problem with networking protocols is if you have that kind of routing, if things are misconfigured, you can get a loop, and then a packet could just like exist forever in a loop. And so the way you fix that problem is with a time to live, and every time it hops, it decrements that TTL by 1, and if it gets to 0, you don't forward it. That fix the infinite loop of a packet. And so those are the first 3 bytes. Let's go back to IMHex. So here we said that this was the type field. And so we're going to right click and say place pattern, built-in type, single, and I'm just going to call it a U8. And so there we go. And now I can name it, which I need to remember. Okay, version. Oops, go back to 5. Version. There we go. Oh yeah, and then there's this option that I'm going to put in here that is going to make obviously it doesn't matter for our 1 byte field here, but for other multi-byte fields, we're going to basically set the interpretation that's going to show up down here in the value part of our pattern data. It's going to by default interpret all of our data types as big endian, which is important. So over here in this pattern editor, we're kind of defining the protocol definitions, and we're doing that by, yeah, again, kind of stepping through here. So then we have 04, which let's just go, okay, remember, this is the type. Okay, and what's cool here is we can go up here, and we can see up here in this message type enum that we can see that 04 is a message. All right, so we're on the right track. We're sending a message. That all makes sense. So let's go back over here. We have our type and our TT and our TTL, our time to live. So again, I'm going to go right click, place pattern, built-in type, single. I'm going to do the same thing for this one. There we go. We have our type field, our caps on. And then time to live. There we go. All right, so we already have those 3 values interpreted here. And you can see it kind of color codes everything, and those correspond down to this pattern data section. Let's keep going. Then we have an 8-byte timestamp, and it is and then again, it's nicely telling us here in this comment that it is unsigned integer 64-bit. And again, big endian. That's important. So let's go ahead and grab the next 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. And then the really cool thing that we can do is we can come over here and we can see that this makes sense, because over here, this uint64 it starts with 175, which if you're familiar with like Unix timestamps, so if I just go over here and I get, my current time in Unix time, you can see that it is, it starts with 175, and so that corresponds to roughly the current time in Unix time, and in our case, it is the number of milliseconds. So right here displayed on DuckDuckGo, that's the number of seconds since January 1st, 1970. But over here, it's just multiplied by 1,000, and so this is the number of milliseconds since January 1st, 1970. So yeah, so it's going to be that data type, and again, go right click, place pattern, built-in type, single, and in this case, we're going to say U64. We're going to call this timestamp, and it is interpreted, and again, because we have this like pragma endian big, you can also manually just go like big endian and tell it individually to be big endian. That's fine, but we're just defaulting everything to big endian, so that should work. Awesome. So now we move on to the next step in our protocol. Why am I going to the wrong place? Here we go. The flag. Okay, so here we have a kind of a bitmap here, but we're just going to represent it as 1 byte because in our case it is going to be set to 1, I believe. So bit 0, we are going to set that bit, but we're not going to mess with a signature or compression just to keep things simple. And so, yeah, this byte that we're going to send, yeah, as you can see, 01. So that means that there is a recipient. Now, spoiler alert, the recipient is like effectively a broadcast address, right? But let's first go and place pattern, U8. Let's call that flags. There we go. What's our next field? So we have our flags, and then a payload length. And again, this documentation is super helpful. uint 16 big endian. So we can go in here, grab this, right click, place pattern, U16, there we go. And so this, it says 74, so there's 74 more bytes. I think it's like not including this thing. So I think it's like this forward. It's not including some part. Oh, I don't think it includes this either. There we go. There we go. And you can see it shows me how many bytes I'm highlighting down here. It says 74. That's matching our length. So this length is not including all of this stuff. So let's keep interpreting. Okay, now it says there's a variable section, which is kind of funny because it says there's a variable section, but then this is fixed. So there's an 8-byte sender ID that is next. So we go 1, 2, 3, 4, 5, 6, 7, 8. And you will notice that this is ASCII, and I've defined it as a dead beef in ASCII, which gets converted to this 8-byte thing here. And so we will go ahead and say place pattern built in, and we'll say an array, and we'll just, yeah, we can call it a char array. There we go. And this is, what is it called again? The sender ID. There's our sender ID. Nice. And there we go. Because we defined it as a char array, it is interpreting it as a string, and it says dead beef. So awesome. Looks good. The next thing we have is if the recipient ID flag is set, which ours is, because remember the flag was set to 1, and so that is saying that has recipient is true. So we're going to have an 8-byte recipient ID. Well, what's this? It's the broadcast address, right? And if we look through the code more, you basically find out that you can either send a direct message to somebody by specifying their recipient ID in this field, or you can send it to everybody with all Fs. So again, we're gonna go and say built-in type array, and we're just gonna say that it's a U8 array, and we'll call it, let's copy from here. Recipient ID. There it is. Excellent. So now we have a few more things before we get to our message. So there is some encapsulation going on between the bitchat message and then the whole binary protocol, which has a message as its payload if the type here is set to 4, which is the message type. So let's keep chugging through this. Okay, so there's a variable length payload, and then there's a signature if the signature is enabled, which we don't have. So now we just have payload. So this is cool. Again, oh yeah, like we said, 74 bytes. So our length field, we know we're interpreting our length field correct up here. So now we need to start looking at a different source file inside the Android source. Now we need to look at the bitchat message. And so again, it's nicely commented. I think these comments carried over from the iOS application. And so the first byte is a flag. And so the flag values, I believe, are defined, yeah, somewhere else in this file. Aha, yeah, here we go. So here are the definitions for our flags. We'll look back at those in a minute. So there's a 1 byte. Yeah, it does that sometimes. All right, there's a 1 byte flag here. Let's go ahead, place pattern, U8. We're just gonna call this, this is more, M flags. So the message flags. There we go, and then back over here. So that value is set to, hex 10, and right here we can see that says that the sender, that we're setting the sender peer ID. Oh wait, that's hex 10. That's not right. No. That's bit 1. No, that's correct. No, it's in hex. I thought I was getting my hex and my integers messed up there. All right. So that means that the one flag that's set in this message that we're interpreting is this sender peer ID, which is basically where you identify yourself as the sender. And so that is like an optional part of the packet, technically according to the specification. So but we're going back up to the message format, and next we have another 8-byte timestamp, another one. Why are there 2? I don't know. Okay, but we go 1, 2, 3, 4, 5, 6, 7, 8. And again, we have this sanity check here that this looks like a Unix timestamp. Right click, place pattern, single, U64. There we go. And we'll call this M time stamp. Bingo. There we go. Now we have 1 byte, I believe. This is the length of the ID. And so you'll notice that this is the message ID, and you'll notice that we see some ASCII that is basically just a UID, right? So we have a length, and then, so this is going to be like our ID length. Place pattern, ID len, and then this. And then what's cool here that we can do is, so that's telling how much the next chunk of the packet, how long it's going to be, because it could vary. And so what we can do is we can take this and we can say place pattern, and we can say that it's an array of chars, because that is all ASCII data. But instead of having it be hard-coded, right, like it is now, here to 24, is we can actually take ID len and pop it in here. And then you can always hit this play button to like reanalyze everything down here, and then that gets properly checked. So if you had, if it did have like a bigger or smaller value there, our decoding should be able to handle it, which is kind of cool. Now let's go to the next one, and that is another length field. So next we have the sender length and the sender data. And so again, here it's just that self-identified name. And so we have here the length byte for the sender. So we'll go there, we'll call it sender length. Cool. And then the next part of that, right there, place pattern, an array of characters. And we put that sender length in there. Just super nice to be able to do that. There we go. And now we have another field here. Okay, so content length. So now we get our content, our data, the actual message. And so there's a 2-byte length field, and then the content comes after it. So we have right here a uint16 type, place pattern, same thing, right up there. Got it. We're going to call it, content length. We'll just call it content because that's what it calls itself. And then we have the content right there. And I suppose the content could be binary, but we're just going to call it a char array. And we'll put that length field in there. So that parses correctly. And then, oh yeah, and then we have the optional fields based on the flag. So again, like we mentioned, the one flag is the peer ID. And so that's how we know this is a peer ID. So there's a length right here. do U8, peer ID len. We're almost there. All right. And then the last bit here, place pattern, an array of characters. I guess yeah, characters, that's fine. We'll just call this the peer ID, make sure the length is what goes there. And we now have decoded our entire protocol, which is pretty awesome. And so we could put other messages in there, and we could copy this kind of pattern definition here. Let me clean that up. And then we would be able to automatically decode packets that had different, values and stuff like that in here. And again, being able to handle a variable length field is pretty clutch in this kind of definition over here. So very impressed with this tool, and it definitely helped me in the development of our Python script. So now what I'm going to do is show our bitchat-spam script here. And so very simply, at a high level, what this does is it uses the Bleak library, the BLEAK library, to perform all of the Bluetooth interactions. And so I have a couple of functions here. So one packet that we did not reverse engineer in this video, and you can go look at the source code to kind of understand it, is this announce packet. And that is how, in the application, the other users show up here, right? So you send an announce message, and then you can see that they are in your network, that they are like actively around you with the bitchat application. So that's what the announce packet does. So this application will announce yourself, and then it will broadcast a message, and you can set the TTL. By default, it's 3. You can set the sender ID, and you can, or actually the sender ID is hard-coded. It is hard-coded to deadbeef. You can change that right here if you want to, but you have to change that in the source code. And the command line parameters, though, allow you to set the sender name and the content, which is kind of cool. And the number of times to send the message. So down here, what it's going to do, we have coded in here the service UUID. This is how the application scans for all the Bluetooth devices around it and knows which one is like advertising that it supports bitchat. That's what this UUID is for. And then the specific characteristic, the place that you like write data to interact with the service, is this UUID, which they were both pulled from the Android source. And so what we do is we do a discover. We scan for devices around us, and then you set, and then this is the way right here is the way you say it, like, hey, do you have that bitchat service UUID? And then we loop through all those devices that do meet that criteria. And then I do kind of a secondary check to make sure that it has this characteristic that I like. You enumerate all the characteristics. If you're not familiar with Bluetooth Low Energy, think like API endpoints. It's like a self-documenting, or it's like the devices just like tell you what API all the endpoints are. And so that's what a characteristic is. And you can enumerate them. And so we check to make sure that that characteristic exists on the device after you connect to it. And then it will go through, and if that's all good, then we will send that announcement packet, and then for, however many packets you want to send, it will send the messages using the code right here. So, and again, this is going to take in a couple command line parameters. It's going to take in a number of how many messages to send, your sender name, what name you would want to identify as on the app, and the message to be sent. So, with that, let's open up our application here. We'll open up a couple of them. Make sure they're online, because like I said, they do get kind of buggy sometimes. All right. All right, we'll just do it right here, and then we'll navigate away. All right. So here we're gonna send a couple of messages. We're gonna be hacker man. We'll just send hello world, and we'll send 10 messages there. So we're scanning. Oh, there we go. And there are all of the messages that we're sending. And again, the way that we implemented this was the protocol that we reverse engineered is all implemented in this second function here, generate message packets. So a lot of these structs and things that we're packing together to form a message packet that we send out is exactly what we reverse engineered here. And so we're forming that packet together. We're putting a valid timestamp that is like the current timestamp in the 2 different timestamp fields, because there's 2 of those for some reason. And so that is how we're able to send all these messages. And you could also have the script change the name every time. It doesn't seem to require that you send a different announcement for you to identify as a different name for the broadcast messages, which is interesting. So you could be sending messages for a name that doesn't even exist over here in this list. That's something you could also do with the Python script. So I will put this in the link in the description. I want to thank you for watching this video. It was a bit of an adventure for me to explore this protocol and the Android app and stuff like that. So let me know if you like this content. Definitely check out the GitHub repositories down in the description. Thank you and have a good day.